Chapter 5, Energetics and Thermochemistry. So in this chapter, we want to talk about the energy change during the chemical reactions. That's why the topic is energetics. And usually the energy change during the reaction that we have is thermal energy. So the heat change during the chemical reactions. And that the name of the thermo comes from. So we have thermochemistry. So we want to talk about the energy change in the chemical reaction. You had it in grade 9 when you studied about the endothermic reactions, exothermic reactions, how the energy change in those reactions. But here we want to talk about the energy change in the chemical reaction in more detail. And we want to measure the energy change. So the measuring energy change is the topic for the first section of this chapter. So you must know these concepts at the end of this chapter. The first one is the heat. The heat is a form of energy. Okay, it's thermal energy. The temperature. In chapter 1, you had the definition of temperature. It says temperature is a measure of average kinetic energy of the particle. It means if the average kinetic energy of the particle is increased, the temperature of that substance is higher. If the average kinetic energy of the particles of any substance is low, that substance has low temperature. Okay, in the chemical reaction, the energy converts, so the total energy is conserved in chemical reaction. It means the energy cannot be destroyed nor produced during the chemical reaction. So the chemical reactions that involve transfer of heat between the system and surrounding are described as endothermic and exothermic. Later on, we will talk about the endothermic and exothermic reactions. And for the measuring this energy change, we introduce the new concepts here in this chapter, and that is enthalpy of a chemical reactions and its unit, which is kilojoule per mole. Okay, so you will be familiar with these concepts. Let's start here by introducing the energy. Energy is a measure of ability to do work, that is, move an object against an opposing force. Okay, so this is the definition of the work. So the work is to move an object against an opposing force. For example, if you lift your laptop from the table, what you are doing? You are doing work against what? You are doing the force against the gravity. The ability to do this is called the energy. Okay? So the energy is ability to do work. The energy that we want to discuss in the chemical reactions are heat energy. The heat is a mode of energy transfer which occurs as a result of the temperature difference and produces an increase in disorder of how particles behave. So the heat means energy transfer. So the heat is not form of the energy. We have thermal energy, which is the form of energy, but the heat is transfer of the energy. Okay? So how this transfer of the energy happens between two objects? Suppose you have the object A and object B, and they are joined to each other, or they are in contact with each other. How the energy transfers from A to B? How thermal energy goes from A to B? This can happen, this energy transfer can happen if you have temperature difference. So for example, if A is 10 degrees and okay, let's say the A is 20 degrees and the B is 10 degrees. How the energy transfers? Energy always transfers from the hotter object to colder object. So the heat is a mode of the transfer of energy which occurs as a result of the temperature difference. What happens when the thermal energy transfers from A to B? What happens to the particle of B? What happens to the temperature of B when energy transfers to that?
Increases.
Temperatures get
Temperature increases. So when its temperature increases, what happens? It means its kinetic energy has increased.
Increases.
Yeah, its average kinetic energy is increased. So it means the particles now in the object B is moving faster. When the particle or molecules moving faster, it means the molecules or particle becomes disorder. Okay. So these are the concepts that you must know. You must know what is the heat, what the temperature represents, and what happens if you have two objects at different temperature. The energy transfers from the hotter object to the uh, colder object, and it increases the temperature of the colder object. So disorderness of its molecule is increased. But let's go and talk more specifically about the chemical reactions. This is very general. These about the concepts of the energy, heat. You have it in the physics, you have it generally in the science. So let's go and talk specifically about the chemical reactions that we have. So to talk it more specific in the chemical reaction, you must distinguish between the system and surrounding. So what are the systems? Who has physics this term? Nobody
no,
has. Okay, so you probably have studied about the systems and surrounding, or in the ESS, maybe you have studied about the system and surrounding. Okay, so the system is the area which the change happens that, or the area that we are studying there. Okay, so if, for example, a chemical reaction happens here, the chemical reaction is our system. Okay, suppose you have a test tube, and inside the test tube you have a chemical reactions. Those reactant and products are our system. Okay. What else is surrounding? Okay, so look at here. It says it is useful in these cases to distinguish between the system, the area of interest. So the system is what we are studying, that one. So that's important for us. Okay, and what else is surrounding? So for example, if we are doing a chemical reaction in the test tube, the reactants and products are our system, and the rest of the material are the surrounding. The test tube is the surrounding. The table that we are doing the experiment on, that are surrounding. So based on this definition, we can have different systems. The first systems are open systems. In the open systems, they can exchange energy and the matter. So what does it mean they can exchange the energy? Suppose a chemical reaction happens inside this test tube, okay, and the reaction is exothermic. So what happened to the energy? Energy is coming out of the system. So we have energy change. And if you touch this test tube, you can feel that it becomes hotter. So this shows that the system has energy change with the surrounding. Your hand here is a surrounding. Okay? And also they can change the matter with the system. Suppose in this reaction a gas forms, for example carbon dioxide, and carbon dioxide can escape from the reaction and go to the surrounding. So these type of the systems, we call them open systems. So they can change the energy can go into the system, the energy can come out of the system, and also the matter can be changed. The different chemicals can go into the system and can come out of the system. The next type of the system are closed system. The closed system, they can do energy change, but the matter cannot be changed with the surrounding. So for example, if I put the lid here, I don't let the carbon dioxide to escape from the system. But if you touch this test tube, still it is hot. So it means the matter cannot be exchanged with the surrounding, but the energy can change with the surrounding. So that's why when the reaction happens, you can feel that, for example, test tube becomes hotter, becomes colder, because it can change the energy. These systems are called closed systems. And you have one more systems which is not mentioned here, that is isolated system. We have isolated system. The isolated systems are the system which neither the energy nor the matter can be exchanged with the surrounding. And we usually don't have this type of the reaction in the chemistry. And this isolated system, we usually discuss it in the physics. So any question about the concepts of the system and surrounding and the type of the systems?
No.
No. Okay. So another important concept that you must know, that the energy is conserved in the chemical reaction. It means although when the reaction happens and the energy goes out of the system, and you can see that the reaction vessel becomes hotter, but the energy is conserved. It means you have not created the energy here. Okay? But where that heat comes from, if you are not created the energy by chemical reaction?
Surrounding? From surrounding?
No. Okay. So if the reaction happens inside this system, okay, and the reaction is exothermic, okay, it transfers the thermal energy to this test tube, and if you touch here, it transfers it to your hand. Okay. It means the energy has transferred to your hand. But we said in the chemical reaction, energy is conserved. It means the energy is neither made nor destroyed. So where that energy comes from then? If you have not made or created the energy, why you feel the test tube to be hot? Okay, that energy comes from chemical potential energy. Where are those chemical potential energy stored? They are stored inside the bonds. So during the chemical reaction, a lot of bonds broken and a lot of bonds forming. Okay, so the breaking the bond and the forming the bond, they are exothermic and endothermic processes. So the heat that you can feel actually comes from the energy which was stored inside your reactants. So your reactants has some energy. When the reaction happens, they can lose some of their energy, and the chemical energy which was stored in your reactants is now converting to the thermal energy and transfers by heat to your hand. Okay, so it means you have not created the energy, just the energy which was stored inside the bond of your reactant is now converted to the thermal energy, and you can feel that one. Okay, so the energy is conserved here. So if the reactants energy converts to the heat energy, what happens to the energy level of the reactants then when they convert to the product?
Decreases.
Exactly. So their energy decreases because some part of energy is converted to the heat energy. So it means you have not created the energy. The energy of your reactant is decreased when they convert to the product, and this amount of energy which is decreased is converted to heat energy, which you can feel. Okay, so this means we can say that in the reactants or in the particles that we have in any material, some energy is stored there, okay, which can convert to heat energy. Okay, so to that heat content of the system is called enthalpy. So the enthalpy is heat content of the system. The definition of the enthalpy is given here. So look at the definition of the enthalpy, which is written at the left side of your book. It says enthalpy, which you show it by the H, is a measure of the amount of heat energy contained in a substance. So some substance, they have some amount of heat energy, but where is that heat energy content of a substance. It is stored in the chemical bonds and intermolecular forces as potential energy. It means chemical potential energy. So the chemical potential energy which are stored inside the bonds of the reactants or on the systems, it's better to say, and it also stored in the intermolecular forces, they can convert to the heat. So we can say our system has some heat stored in that, and that heat is called enthalpy. Okay, so what happens then? It says when substances react, the difference in the enthalpy between the reactant and product result in the heat change which can be observed. Okay, so for example, suppose this is the energy, and the energy of the reactants are here. I show it by R. When they convert to the product and you check the energy of the bonds in the product and you add all of them, and you can see the product's energy are here. So what happens to this energy? You can see that the energy which was stored inside the reactant is decreased when they convert it to the product. So this decrease in energy is the heat energy, which gives to the surrounding. Okay? The opposite things also can happen. Suppose if you check the energy of the reactant, the energy of the reactants are here. And when they convert to the product, you check the energy which are stored in the product are here. What happened to the energy? Energy of the system has increased. So where that energy comes from here in this case?
اندوترمیک باید باشه دیگه هیت بر میداره مگه نه
از کجا؟
از سراوندینگش دیگه
Exactly. So it takes the energy from the surrounding. So what happened to the temperature of the surrounding?
decreases
Decreases. So you can see that, for example, the test tube becomes colder. If the test tube becomes colder, it means the process was endothermic. Energy has gone into the system from surrounding. Okay. So if you feel the test tube to becomes hotter, it means the energy comes out of the system. Okay. So based on that one, you have the energy change. Okay. So if, for example, the energy content of the reactant is here and we call it H1, or and the energy of the product are here, we call it H2, because the H or enthalpy represents the heat content of the system. So this difference is called delta H. This is what we can see. It's very difficult to identify what is H and what is H2. But the difference between them is easy to understand because it transfers the heat to the surrounding and the temperature change. If you measure how much temperature is changed for the surrounding, you can know how much heat is transferred to the surrounding. It means this difference between the reactant and product. So what we are measuring is the delta H of the systems. Okay, so let's go to the next page to show this on the diagram. Suppose a chemical reaction is happening here. Reactant is converting to the product. So the energy content of the system before reaction is here. So it's H1. After the reaction happens, the energy of the system was here, H2. It means the energy of the system has increased. But where that energy comes from, it comes from the surrounding. So the energy has gone into the system. Okay. So if we want to show the energy change or delta H, which is energy content in the after reaction minus energy content before reaction, you can see the H2 is bigger than H1. So the delta H is positive here. Delta H positive. And it represents the endothermic reaction. So the endothermic reaction is the reaction which heat goes from surrounding into the system, and the energy content of the system increases. The product has more energy than reactants. So what happens to this test tube? What happens to its temperature?
Decreases.
The temperature decreases. So you can feel that the test tube becomes colder. Even this water that you have inside it, this water is also surrounding, okay? The solution, the solvent is surrounding, because the reaction happens inside the water, but the water doesn't participate in the reaction. So the water is not reactant, the water is not product. So the water is also considered to be surrounding. So the energy from the water goes into the reactant when it converts to the product. So you can see the water also here becomes colder. So in the endothermic reaction, what is not system becomes colder. But the system doesn't become hotter. The energy just stored as a chemical energy there. Okay, so always the change in temperature happens for the surrounding, not for the system. But in the next one, the energy before reaction was here, so this is H1. Energy after reaction was here, so this is H2. So you can see that energy is decreased. It means the system has lost some energy. Where that energy which is lost goes, it goes to the water, it goes to the test tube, and if you touch here, it goes to your hand. So you can feel that the reaction vessel becomes hotter. Okay? And if you want to find the change in energy content of the system, H2 minus H1, H2 is smaller than H1, so the delta H is 0. So if the delta H or the change in enthalpy is 0, it means the reaction was exothermic, and in the exothermic reaction the surrounding becomes hotter. Okay, so any question about these exothermic and endothermic reactions?
No.
It also shows the same graph here, but here is written reactant converts to the product, reactants convert to the product. Okay, so this is very important to distinguish between them. They give you these two graphs and they ask you if the reaction is exothermic or endothermic, what is your evidence? Okay, so one of the evidence is that delta H is negative. Another evidence is the energy level of the product has decreased. So it means the energy has gone out of the system. So when the energy goes out of the system, it's exothermic. Exo means out. Here, the reactant, when it converts to the product, the energy of the system has increased. So it means the energy going into the system. Okay, we call it endothermic. Endo means into. Okay, and the delta H would be positive. Okay, so it's very important. It's written here. It says for exothermic reactions, heat is given out by the system and the delta H is negative. For the endothermic reaction, the heat is absorbed by the system and the delta H is positive. And in either of these change, what happens when you touch the reaction vessel? In exothermic reaction, you can feel that the reaction vessel becomes hotter. In endothermic reaction, you can feel that the reaction vessel becomes colder because the energy gone from the surrounding, from the reaction vessel into the system. Okay, so on the next page, what is different, what is defined here is S standard enthalpy change. So enthalpy change means delta H, how the energy change during the reaction. When we say the S standard, we usually put a note here. So you can see this sign here, a delta H note. Okay, this means S standard. So what is S standard enthalpy change? It says as the enthalpy of the system depends on the intermolecular forces of the reactants and products, the enthalpy change for the reaction depends on the conditions under which the reaction occur. So it means if the reaction happens at the pressure of 1 atmosphere, the delta H of the system would be different if the same reaction happens at the pressure of 2 atmosphere. So it's very important when we say, for example, the delta H of the reaction is, for example, negative 345 kilojoule per mole. At which conditions we are measuring this change for the reactions? So most of the time, we have standard conditions and we report the enthalpy change for any given reaction at the standard conditions. What are standard conditions? It's written here. A pressure of 100 kilopascal, and if you have the solution, the concentration of the all solution must be 1 mole per decimeter cube, and all substances are in their standard state. Okay, what is means that all substance must be in their standard state? It means if you have the water and these conditions, it must be liquid. Okay, you cannot have the ice, for example, there, because then this delta H is not a standard. So if you have, for example, the nitrogen in the chemical reaction as a reactant or the product, it must be in the gas state. Okay, so all substance must be in their standard state. So what variable is missed here when we define the standard conditions? We have pressure, we have concentration, and
Temperature.
temperature, exactly. So the temperature is missed here. So that's why when we are talking about the delta H at a standard condition, you must mention at which temperature you have measured this one. What was initial temperature of the reaction before happening? But most of the time, the temperature is defined to be 298 Kelvin. Okay? So this is a standard temperature, but it's not a part of definition for the standard state. But it's usually we assume that the temperature is 298. We call it room temperature. So it's 25 degrees centigrade. Okay, so this is considered to be room temperature. But you must know that the temperature is not defined in the condition of the standard. In the standard conditions, you only talk about the pressure, about the concentration, and about the state of the material. But most of the time, when we don't mention the temperature, it means we have done the experiment at room temperature or 298 Kelvin. Okay, so let's talk about two examples. Here is written thermochemical equation. So as we said, the thermo means thermal. So thermochemical equation, what is the difference between thermochemical equation and chemical equation? In the thermochemical equation, they give you the delta H. So if the delta H of the reaction is given, it means what is given to you is thermochemical reaction. So look at this reaction. What do you have here? What is CH4?
Methane?
The CH4 is methane. It reacts with oxygen. So this is burning. Okay. So you know that the burning is exothermic process. It produces a lot of heat. So look at the delta H. The delta H is negative. And what is the unit? Kilojoule per mole. So usually the delta H is measured for 1 mole of the substance. It's measured per mole. So what this means, delta H for this reaction is negative 890 kilojoule. It means if 1 mole of methane reacts with 2 mole of the oxygen to produce 1 mole of carbon dioxide and 2 mole of the water, the amount of heat which released is negative 890 kilojoule per mole. Okay, if you have 2 mole of the methane and react with 4 mole of oxygen to produce 2 mole of carbon dioxide and 4 mole of the water, how much heat is released?
Double the amount?
2 times 890, twice as this one. So this one, which is written per mole, it means for these stoichiometry of this reaction. If you multiply all of them by 2, instead of having 1 mole of methane, you have 2 mole of methane, the amount of heat energy which releases is twice as that. Okay, clear?
Yes.
Okay, so let's move for this one. What process is shown here? It's photosynthesis. You know that the plants can use the sunlight energy to make the substance. So what happened to the energy? Energy goes into the system. So this is endothermic process. And if you look at the delta H, it is positive. So for this reaction, it's positive 2,802 kilojoule per mole. It means if 6 mole of the carbon dioxide reacts with 6 mole of the water to produce 1 mole of sugar and 6 mole of the oxygen, it needs 2,802 kilojoule of energy. If you want to react, for example, 12 mole of carbon dioxide with 12 mole of the water to produce 2 mole of sugar and 12 mole of oxygen, how much energy do you need? 2 times 2,802, twice as this one. Okay. The standard state is defined here. It says a standard state of a substance is the pure form of the substance under standard conditions. Okay. And what are standard conditions? These are standard conditions, and usually the temperature must be 25. Okay, so we had the temperature on the first chapter. Here, one more time, we talk about that one. The temperature is a measure of average kinetic energy of the particle. So if you have, for example, a block of iron, it composed of the sea of electrons, a lot of delocalized electrons, and metal atoms or metal ions. And you know that in the solid state, these atoms just vibrate in their position. So they have some kinetic energy because they are moving. But if you look at each of these particles, some of the particles vibrates faster, some of them vibrates slower. So not all of them has same kinetic energy. But if you look at this particle, if you look at this block of the iron, the temperature is uniform all over that block of the iron. Okay? So it means the temperature is average of all of these movements. Although some of them move faster, some of them move slower, some of them has higher kinetic energy, some of them has lower kinetic energy, but the temperature shows the average of all of these kinetic energies. Okay? And most of the time, the unit for the temperature that we use is Kelvin, okay, which we can easily convert it to degree centigrade, or if the question is given in degree centigrade, we can easily convert it to Kelvin. Okay, so I want to talk about heat change based on the temperature change. Okay, so let's go back here. So suppose you have a block of iron, as I said, okay, and heat is going into this block of iron. Okay, so I can show heat by Q. Okay, Q means the heat energy. Okay, so I write it here, heat energy. How can I know how much heat energy is transferred here? What happens with the heat energy goes into the block of iron?
آقا کینتیک انرژیش زیاد میشه تمپرچرش هم زیاد میشه.
Exactly. So what we can see is that its temperature is increasing. Okay, so if the temperature is increasing, it means the heat has transferred into that. But how do you know how much heat energy is transferred there? It depends on what? So you said its temperature is increasing. So when you transfer the heat, you have the temperature change. For example, the temperature from 10 degrees increases to 20 degrees. But the amount of the temperature change or the delta H depends on what?
Mass.
Okay, so how the change in temperature of the iron depends on its mass.
خب اگه مس بیشتری بخواد تمپرچر بیشتری میخواد که بتونه
نه نگاه کن نه temperature بیشتر اونجوری نه. So I say if you transfer the heat to the block of the iron, its temperature increases. But how much its temperature increases? It depends on what? You said it depends on the mass of the iron. How
The
the
amount of heat given to it.
Okay, so yeah, one of them, the delta T depends on the amount of heat. If you give more heat to the system, its temperature increases more. So the delta T would be bigger. Okay, so this is one thing. What else? The mass of the iron. How the change in the temperature of this iron block depends on its mass.
Distribution-ish.
No,
Distribution heat.
I means if the mass of the iron increases, what happens to change in its temperature? Is change in temperature
کمتره.
کمتره. چرا؟
چون که دیگه باید بیشتر مثلا جای بیشتری رو داغ کنه.
تعداد پارتیکل های بیشتری داریم اونجا. Okay, so it means the change in temperature is inversely depends to the mass. Okay, so if the amount of heat which you are transferring to this iron block becomes more, the temperature of the iron block also increases more. If the mass of this iron block that you have here was smaller, the increase in its temperature was bigger. It means the change in temperature is oppositely depends to the mass. Okay, so the change in temperature depends to the amount of heat, but it's inversely depends to the mass of that one. Okay, the amount of heat also depends on this block or the material that you have here. If you transfer the same amount of the heat to 1 kilogram of the iron and same amount of the heat to 1 kilogram of the copper. So for example, you are adding 10 kilojoule of the heat to 1 kilogram block of the iron and 10 kilojoule of the heat to 1 kilogram copper block. When you check their temperature, the increase in temperature are different from each other. This means the amount of temperature change also depends on the material that you have there. Okay, you are transferring the same amount of energy to the same mass of two different materials, but their change in temperature are different. Okay? So it means the type of the material and what do you have also is important there. So we show it by the C. So the C is a quantity which depends on the type of the material. We call it specific heat capacity. Specific heat capacity. It means different material has different specific heat capacity. But what is the definition for a specific heat capacity? So the specific heat capacity is the property of a substance. So it depends to the type of the substance. The specific heat capacity for the iron is different from the specific heat capacity of the copper. It's different from a specific heat capacity of the water. Okay, which gives the heat needed to increase the temperature of the unit mass by 1 kilogram. The unit mass, for example, let's say 1 gram of the substance. So the specific heat capacity for any substance is the amount of heat needed to increase the temperature 1 gram of that by 1 Kelvin. Okay. Suppose you have two substances with different specific heat capacity. Let's say one of them is a specific heat capacity is 4. It means 4 joule of energy is needed to increase the temperature of 1 gram of that by 1 degree centigrade. And you have another substance with its specific heat capacity is 2. It means if you want to increase the temperature of 1 gram of that substance by 1 degree centigrade, you need 2 joule of the energy. Okay, so you have two substances. One, its specific heat capacity is 4. Another one is its specific heat capacity is 2. And
آقا
you
مگه با 1 کلوین نبود نوشتین 1 سنتیگراد.
Yeah, it can be Kelvin, it can be same. If you change the temperature 1 Kelvin is same as if you change the temperature 1 degree centigrade. Okay, the change
پس
in
اگه
temperature,
هر کدوم بنویسیم درسته؟
yeah, the change in temperature in Kelvin and degree centigrade are same.
اوکی.
Okay, so if you have two substances, their mass is same, 1 kilogram, 1 kilogram, and you are adding the same amount heat to both of them. Which one its temperature increases more?
The right one?
The right one. Yeah, the right one. Why? Because for each gram of that to increase its temperature, you need only 2 joule of energy. But for the left one, for each gram of that, if you want to increase its temperature by unit, you need 4 joule of energy. Yeah, you need more energy to increase the temperature of the left one. So the substance that has a smaller specific heat capacity, its temperature change more than the other one. Okay, so that's why here specific heat capacity is in the denominator. It means same as the mass. If the mass becomes smaller, change in temperature becomes bigger. If the specific heat capacity for substance is small, the change in temperature for that substance becomes bigger, more. Okay, so let's cross multiply these ones. So I give the denominator 1 to that. So what happens then? I can write the Q would be equal to mass times the specific heat capacity times delta T. So what can I measure here? I can measure the amount of the heat which is gone into the system or come out of the system. How? By measuring the temperature change. So the temperature change gives me a measure, or it gives me an idea how much heat is gone into the system or come out of the system. So if I know what is the mass of the system, and if I know what is the specific heat capacity of the system, the specific heat capacity, you have it in the tables in the IB data booklets, or if it's not in the IB data booklet, they will give you what is the specific heat capacity of the substance. Okay, so you know what is your material, so you can know what is your specific heat substance. You can weight that one, so you can know what is the mass, and you can measure how its temperature change. If you multiply all of them by each other, you can know how much heat is going into the system or come out of the system. Okay, but I want to talk about the sign of this one, sign of the Q. You know that the mass is always positive. A specific heat capacity is positive, but the delta T can be positive and it can be negative. So the positive means the temperature of the substance is increased. Negative means temperature of the substance is decreased. Okay. So if the temperature of the substance is positive, the Q also becomes positive. If the change in temperature is negative, or it means if the temperature of the, for example, block of iron is negative, the Q also becomes negative. Okay, so the sign of the Q depends on the change in temperature. If the temperature of the substance increased, it means the energy has gone into the system. If the temperature of the substance is decreased, it means the energy has gone out of the system. Okay, and at the bottom, these equations are given to you. The heat change, Q, depends on the mass, specific heat capacity, and temperature. Okay, the unit of them are important. The mass is gram. The specific heat capacity is joule per gram per Kelvin or per degree centigrade. And the temperature is in Kelvin. So what happens if you multiply all of these? This gram in numerator cancels this gram in denominator. Kelvin in numerator cancels this gram in denominator. So what happens? What remains here? The joule, unit of energy. Okay. So the formula is given also here. And for the water is very important. Its specific heat capacity is 4.18 joule per gram per Kelvin. This value is given in the IB data booklet. So I think in the first table in the data booklet, you have the specific heat capacity of the water.